Hey folks, Ms. Gosling here. In this video, you're going to learn about the work-energy theorem. By the end of the video, you'll be able to solve problems involving the work-energy theorem. So let's go ahead and get started. We're going to start by talking about what even the work-energy theorem is. So the work-energy theorem states that the work done on or by a system is equal to the change in energy of that system. In other words, work, W, is equal to delta E, with delta meaning the change in energy. So one example of work being done is a crane lifting up an object because the potential energy of that object is changing. It's in fact increasing because the crane is doing work on the object. Another good example of the work-energy theorem in action is a car accelerating. So the kinetic energy of the car is increasing, and as a result, and that is happening because work is being done by the engine on the car. So let's talk about one example. So our first question is how much force is required to lift a 10 kilogram box up 2 meters. So we could solve this by using our definition of work, but instead we're going to use the work-energy theorem to solve it. So let's start with our givens. So from this problem, we know that the mass of the box is 10 kilograms. The height that it travels is equal to its displacement, and that's going to be 2 meters. And we know little g is 9.8, and we're going to do little g positive because we're worrying about energy, which again is a scalar, not a vector. Our unknown is the force the force required to lift up that box. So for this question, we're going to use the work-energy theorem to solve our problem. So I know that work is equal to my change in energy. In this case, I can expand out my equation. So I know that work is equal to force times distance, and my change in energy is my final energy minus my initial energy. Initially, I have no energy. When I go to the top, my box isn't moving, but I do have potential energy due to gravity. So what I can say is that force times displacement is equal to my gravitational potential energy at the end minus my initial energy, which is 0. Of course, I can also cross this off and just write that FD is equal to UGF. My force times my displacement, the work done, is equal to my final potential energy. And expanding that out, I can say that the final potential energy is mgh. Or in this case, because I wrote up here that my height is equal to my displacement, I can say that my force times my displacement is equal to mg times my displacement. So let's go ahead and now move towards subbing and solving. So I know that force times displacement is equal to mass times gravity times displacement. So my displacements will cancel. And the force required is just mg, or 10 times 9.8, or 98 newtons. And there you have it, guys. I have solved this problem using the work-energy theorem. So let's do a problem where it's a little more important to use the work-energy theorem, so we don't really have a good substitution for it. So in this question, I am pushing a 10 kilogram car. So here's my car. And I'm pushing at a 30-degree angle over 5 meters. How fast will I be moving when I'm done pushing? So that's the first question. And then how much energy did I use to move the car? So let's go ahead and figure that out. So I'm going to start with the first part of our question. How fast will the car be moving when I'm done pushing? And to do that, I'm going to look at my givens. So I know that the force that I apply is 100 newtons, and I'm applying that at an angle of 30 degrees over a distance of 5 meters. And I know that the mass of my car is 750 kilograms. I'm also going to assume that my car was at rest to start. And that's just something that I should have probably written in the question, but that we can assume if we need to. Now my unknown here is my final velocity. So to solve this problem, I am of course going to be using the work-energy theorem. And what I'm gonna want to do is again expand out my equation. So because I'm applying a force at an angle, I know that my work is equal to FD times the cosine of theta. And then I know that I have kinetic energy at the beginning, or at the end, excuse me. And in the beginning, I also have kinetic energy, though in this case, spoiler alert, it's 0. So expanding this out one more time, I know my force times my displacement times the cosine of my angle. And I'm going to go ahead and cross off that kinetic energy because that is equal to 0. So I know that force times displacement times the cosine of my angle is equal to 1/2 m times my final velocity squared. Therefore, my final velocity is equal to 2 times my force times my displacement times the cosine of my angle divided by my mass and the square root of that whole thing. And this is something you guys should be able to do on your own. If you can't, come talk to me. I'm happy to walk through the algebra here. Regardless, now we are ready to go ahead and sum and solve. So I know, of course, I have solved and found that V final is equal to the square root of 2 times 100 times 5 times the cosine of 30, all divided by my mass of 750 kilograms. And you'll notice, guys, we're in meters, we're in kilograms. If it was in grams or centimeters, we would have to change into our SI units. So now all that's left to do is plug this into my calculator. And when I do that, what I'll find is that my final velocity is approximately 1 meter per second. Now, for the second question, how much energy did I use to move the car? The energy gain in the car is equal to the energy that I have lost. In other words, the work done is equal to the energy that I have lost. Or, a little more clearly, my change in energy is equal to FD times the cosine of theta. Therefore, my energy lost is equal to 100 times 5 times the cosine of 30, or 433 joules. And there you have it, guys. That is the energy that I expended to move the car. So let's go ahead and talk takeaways. First, when work is done on a system, it gains energy. When a system does work, it loses energy. And those are our takeaways. And wow, I have highlighted all of this, but it's because I kept it short and sweet. So again, when work is done to a system, energy is put in the system gains energy. When a system does work, it is putting out energy, and therefore it's going to lose all of that energy. And this is just the law of conservation of energy focused around the energy entering and leaving a system. So with that, you have now learned about the work-energy theorem. It is your turn to solve some work and energy problems. Best of luck and happy solving.